Good morning. I thought I'd just start with a few reminders. Homework 1 was due last night. Therefore, homework 2, which will be on reactor theory, is due next Monday. The request for qualifications response is due this Friday. That is to be submitted, just one response per team. And basically what you're providing is a cover letter and some details about the qualifications of each of your team members. So we will continue, and actually we'll finish reactor theory today, and then we'll be using this material all the way through the semester. We'll start the coagulation flocculation, which will include rapid mixing, on Wednesday, and we'll have about 4 lectures on that. And just a reminder that on Friday, the Center Career Fair, that's a virtual fair, is occurring for civil and environmental engineering majors. And I've provided details both on Slack and on the Google blog. So I thought I'd start with just a simple poll question. We have a poll question here. So the volume of a reactor is constant at 100 liters. A 200 milligram per liter sodium chloride solution is pumped into the reactor at a flow rate of 10 liters per minute. The initial concentration in the reactor is 150 milligrams per liter. And I've asked you for the steady state concentration of sodium chloride. So sodium chloride is non-reactive substance. Sharing the results, you should see those right now. So you can see about half the number of students that responded, 42% said 150, 50% said 200, and a few of you said 100. Actually, I have 100 twice. Okay, so let's look. What do we have? We have a reactor here. And that reactor is 100 liters. The initial concentration in the reactor is 150 milligrams per liter. We're going to pump in a solution that is 200 milligrams per liter at a flow rate of 10 liters per minute. Okay, we'll assume that we have a CSTR, so it's completely mixed. We'll assume that the volume is constant. We have sodium chloride, which would be non-reactive. So the question is, what is C out? And let's say Q out equals Q in equals Q. So let's write a mass balance. Here's our system boundary. So control volume is inside that boundary. So we have the change in mass with respect to time is equal to the mass rate in minus the mass rate out, and we don't have a reaction term. So volume is constant. So we can write the expression. Since you're asked for the steady state concentration, that means that the change in mass with respect to time is simply equal to this. Note, C naught is not in the equation. So what we would see here, if we time versus concentration, we start at time 0 at 150. And that concentration is going to increase exponentially until it reaches 200. So at steady state, it will reach 200 milligrams per liter. And this time will be somewhere between 4 to 5 times the detention time. As I said, note here, okay, because we're looking at steady state, it doesn't matter where we start. It wouldn't matter if I had written the problem that C0 is equal to 10 milligrams per liter. There we would just start at 10 and we'd end up at the same place. Okay, then let's move on. So I want to move on to a situation where we have multiple reactors in series. So looking back, picking up with the problem that we were doing on Monday, I'm basically using the exact same conditions. So we have a 500 cubic meter reactor. We're starting with clean water. So C naught is equal to 0. At T0, we turn the pump on and we start pumping a solution. We have a reactive substance with a concentration of 100 milligrams per liter. The flow rate is 50 cubic meters per day. The volume of solution in the reactor is constant, so V is constant. And the substance degrades according to first order kinetics with a constant of 0.25 inverse days. Now, we showed that when we had one reactor with 500 cubic meters, the concentration leaving that reactor, we have Cn is equal to 100 milligrams per liter. Because we have a reactive substance, the concentration leaving the reactor is 28.6 milligrams per liter. Now, the volume here is 500 cubic meters. Question is, what if instead we have the situation, we still have Cn is equal to 100 milligrams per liter, but we have two reactors in series. So we have a reactor here, 215 cubic meters. We have a second reactor, 250 cubic meters. So the total reactor volume is the same. The question is, what is the concentration leaving? So I just drew it. I'm going to skip this slide. Okay, so let's just look at the situation where we have a CSTR. So we're again looking at a CSTR. We have a series in series with first order decay. Okay. So in the case of the situation we have, each of these is 250 cubic meters, and we said for the problem we're looking at, the initial concentration is 100 milligrams per liter. So we can write two mass balance. Okay. C1 is 100 milligrams per liter. Qn is 50 cubic meters per day. C2 is C out from reactor 1. Volume is constant, so C out is the same. K, we said, was 0.25 inverse days. C2 is C out from reactor 1, and the volume here is 250 cubic meters. So it's the volume of reactor 1. C2 here, notice, C2 here is what the concentration leaving reactor 1, and that's the same concentration entering reactor 2. We're assuming that there's no reaction in that piping between reactors 1 and 2. Qn is still the same. Okay. C3 is C out from reactor 2, and V2 is 250 cubic meters per day. Okay. Now we're only going to look at the steady state concentration. As I mentioned, most of our reactors in water and wastewater systems will operate at steady state. So I've described these as. Okay. So we have, as I mentioned, Q is constant, which means the volume is constant. Okay. At steady state, we can say that this, we've pulled this out, V dc dt, and that equals 0. So if we have steady state conditions, the change in mass with respect to time is equal to 0. And if we substitute in for these equations, and we'll solve for C2, so it's algebra, C2 is equal to 44.2 milligrams per liter. And I'll write this one, okay? So C2 is 44.2 milligrams per liter. Q is 50 cubic meters per day. C3 is what we're looking for. Q is the same. And V was 250 cubic meters per day. And that equals 0. And notice here, I have units. I haven't converted. I could convert in 1,000 liters per cubic meter. I could convert it, but I'm going to have 1,000 liters per cubic meter in every product, so it cancels out. And C3 is equal to 19.75 milligrams per liter. So significantly less. If we go back and we think about the reactor before, we started out at 100, and when we had a reaction with one reactor, we had about 28.6 milligrams per liter. When we have two reactors, so the total volume is the same, we have a lower concentration. So 2 reactors, same volume, 2 reactors is more efficient in terms of achieving a lower concentration than that 1 reactor. Now, we mentioned the other day that detention time is equal to the volume divided by the Q. So we can substitute so that we have detention time in the equation. Okay, so this is the same set of equations where we have 2 reactors in series. And so C2, again, is the concentration leaving reactor 1, and it's also the concentration entering reactor 2. So it's important to recognize that. If we have steady state, this is equal to 0. And what we end up with is this equation right here. Okay? That says that the concentration leaving the nth reactor is equal to the concentration entering divided by 1 plus K times the detention time in each reactor, the sum to the nth power. So we had 4 reactors, each one 125 meters cubed. Each one 125 meters cubed, same detention, same rate constant. So this is equal to, so C to the 4th reactor is equal to 100 milligrams per liter, 1 plus 0.25 inverse days times 125 meters cubed, its whole sum to the 4th. So what if we have 10 reactors, 100 milligrams per liter entering, 1 plus 0.25 inverse days, first order kinetics. We have 10 reactors, so the total volume equals 500. We'll keep this constant. So the volume of each reactor is 50. Take this to the 10th. So the concentration, I'll just write that 10.7. So it's 10.7 milligrams per liter. So we had, with 1 reactor, it was 28.57. With 2 reactors, it was 19.8 milligrams per liter. And with 10 reactors, it's 10.7 milligrams per liter. And the question was, did I put in volume for detention time? And you are absolutely right. I did. Did I do that all the way through? Thank you for catching that. This should be the detention time. Okay. That should be detention. So what was our flow rate? Is 50 cubic meters per day. Our volume for each reactor is 50 cubic meters. So our detention time is 50 cubic meters divided by the flow rate, and it's 1 day. So this here, and this here is 1 day. Thank you for mentioning that. And I apologize for the error. Makes more sense?
So were all the calculations though, were they done with 1 day then for that?
So let's go back here. Let's go. Okay. So here, notice, and okay. So in this case here, notice I have volume. Okay. I haven't written it in the more general form. So in this case, it's volume. So then when I substitute in here, I have, so this was C2 times the flow rate minus C3 times the flow rate minus K times C3, that's C out, times KCV, times the volume. So in this case, it's volume. Okay. Here, when we go to, sorry, this equation here, which here detention time has been substituted for V over Q. So it's basically just a division. So we have dC dt, volume here, equals Q in Cn minus Q out C out minus KC V. If I divide both sides of the equation by V here, then the V cancels, and I end up with Q over V, which is the inverse of detention time. So I can write it here as Cn minus C out, because I can factor that out. V over Q is detention times divided by the detention time minus Kc. So that becomes the general equation. Okay. So from that equation here, we get this equation right here. So at steady state, C, whatever this would be, C4, okay, is simply equal to concentration divided by 1 plus K times my detention time, the sum to the n power. Okay, so it was correct before, where I used volume before was correct. What I did wrong here was right here, okay, that, and I'm going to leave it this way. This is detention time. So let's calculate the detention time. We have 50 cubic meters per day, 125 meters cubed, and that's my detention time that goes in here. So that was wrong here. I apologize. Any questions about this equation here? Because I know you've got a homework problem, and I apologize for making that mistake. But hopefully we've clarified it now. So this was wrong. This is detention time here. Okay. Let's look now at batch reactors. Now, batch reactors are often known as fill and draw. So we have our reactor. Drawing here. We're going to fill it. We're going to mix it. And we're going to empty it. So we fill, mix, and empty. So we're going to allow it to react. We'll make a number of assumptions. We're going to assume that it's well mixed. We will assume that the volume is constant over the time considered. So we're not considering the filling and emptying. So we're ignoring that time that it takes to fill. We're ignoring the time that it takes to empty. The concentration in my reactor is a function of time. And it is not at steady state. Since the concentration is changing, so the change in mass with respect to time is not, in the reactor, is not equal to 0. Okay, so we're going to fill this reactor. We've got some flow. We're going to fill it. We don't worry then, actually, we're really not worrying about the flow. We filled the reactor. We're going to allow it to react, and then we'll empty it. So in this case, the change in mass with respect to time, we'll write the general equation that we've written, first order expression. Since we're ignoring the filling and there's no flow in, we just take from the time that you shut off the pump and the reactor's filled. Since we ignore the emptying portion, then there's no mass out. The only term that we have then is KCV. So we have V dC dt is equal to minus KCV. V cancels, and we have dC dt is equal to minus Kc. So if we integrate this from C0 to Ct, and from time 0 to time t, we end up with the expression ln C over C naught is equal to minus Kt, or C equals C naught e to the minus Kt. It's the same expression. So now we'll go back to the same situation, but now we have that same 500 cubic meter reactor. We fill it with the same reactive substance. We start with a concentration of 100 milligrams per liter, and the substance degrades according to first order kinetics. So we can write a mass balance which change in mass with respect to time is equal mass in minus mass out. Both of these are 0. This is our mass reacted. Since we have, we know by looking at this, inverse time, we have first order kinetics. So we can write this. So we have V dc dt equals minus kCV. V cancels, we integrate, and we have ln C over C naught is equal to minus KT. Okay. So let me ask you this. What is the final concentration? If we allow this reaction to continue, what concentration do we end up with? How does the graph compare? So we have C versus time. We start at 100. No, we said with a CSTR with one reactor, we had 86.6 milligrams per liter. With 2 reactors, notice our total volume is always 500 cubic meters. With 2 reactors, what do we have? 19 point, back to my notes. We had 19.8 milligrams per liter. With 10 reactors, we had 10.7 milligrams per liter. So what are we going to have now? Eventually, it will reach 0. Final is equal 0 milligrams per liter. So eventually, we're going to reach 0. This is a good question. Okay. Is the equation, okay, so the question that some is asking, student is asking, is this always the equation we should start with? Let's think of a situation, okay? Let's look at this with a lake. And let's say we have a river flowing in, and the concentration of some pollutant in the river is 0.1 milligrams per liter, and we have a flow in the river. Okay. Okay. We have a outfall into the lake, and the concentration from the wastewater treatment plant is, let's say, 10 milligrams per liter, and we have a flow from the wastewater treatment plant. Let's say we have a, let's draw this as a river. So we have a river leaving. We have Q out and C out, and we have a reaction term. So we'll assume we have a first order. What's our starting equation? So we have change in mass with respect to time. What's the starting equation here? equal to mass in from the river plus the mass in from the wastewater treatment plant minus the mass out from the river out minus the mass reacted. In all cases, what we've done is we've drawn, and I didn't draw the picture, but here is our system boundary. And this is our control volume inside that system boundary. Does that make sense? Yes, no, did I lose everybody? You really have to think about the system that you're describing. So you need to think about all of the masses. We could have added additional masses. Perhaps there is some pollutant in the rainfall, in which case we need to think about how much rainfall falls and what pollutant is in there. Maybe there is if we added a pump here, so we'll add a pump, and this is going to the city for their drinking water. Now, if that is the case, now we have another mass out from the pump. So each time, rather than thinking of an equation, okay, so the question is, why didn't I use KCV? Notice I put mass reacted. Okay. So the mass reacted, if I have first order kinetics, is equal to K times C in the reactor, in this case the lake, times the volume. So that's the next step. We'll do a number of problems towards the end where I'm going to put you in to breakout groups. And I think it really takes going over these problems, kind of thinking through. Try not to think about what equation should I use. Draw a picture. The first thing you want to do is draw a picture. Okay. And that will help define what equation you're going to use, because you need to first think about what are your masses in, what are your masses out, what is reacting. So let's look at a plug flow system. So with a plug flow system, what we can think about this is, remember, we talk about this plug, okay? This packet of material. And if you think of a train, okay, there's some kind of shown here with the CSTR. As this train moves down the track and it moves along, there is no contact between this boxcar and the one behind it or the one behind it. So each boxcar is totally separate. The mass stays in that boxcar and it's just going to move down the tracks. We can describe it this way here, so with a pipe, and we have a plug here. So when we look at this, we will assume that this parcel is moving down the pipe. we will assume that we have no dispersion. We will assume that, okay, here's my parcel. I have no mass entering, and I have no mass leaving that parcel. So just think of it as a balloon. If I put a balloon in a pipe, and that balloon were to move down the pipe, I would have no mass, assuming the balloon is fully impermeable, I would have no mass moving in and out of that balloon. And that balloon is just going to move down the pipe. It's just going to move, and eventually it leaves the pipe. So essentially what you have is a completely mixed reactor that's moving down this pipe, this duct, this river. Okay, if you took a balloon and you threw it in the red cedar and you pulled it out when it finally got to the confluence of the Grand River. So we're on campus. So here's the MSU campus. Here's the river. Okay, we're going to dump a balloon. Here's our balloon. And it's going to float down the river. And eventually it's going to get to where the Red Cedar meets the Grand River. And it all becomes the Grand River. Okay, here's my balloon. If that chemical were reactive, did the concentration change? So you threw in a balloon, okay, and inside the balloon is a reactive chemical. And you go down to the confluence of the Red Cedar River and the Grand River, and you pick out the balloon. Is the concentration the same? If it's reactive, it will change. The plugs can be reactive or non-reactive. But this, we said it's a reactive pollutant, so it will change. The concentration here at the Grand River is a function of what? It changed with time. And what else? What other term can we think of? Actually, there's two other we can think of. It's related to time. The decay rate. Okay, but let's keep the decay rate constant. Distance, exactly. And velocity. And they were all related. So time, distance, and velocity. So when we look at plug flow reactors, we can look at time, we can look at distance, and if we're looking at distance, we'll typically look at velocity, okay? Because all those terms are related. Now, eventually, it gets out to Lake Michigan. So here's our balloon. And that balloon floated. Oh, now to Lake Michigan. The mass inside, so the mass in my balloon, that's equal, and write the general equation, Do I have any mass entering my balloon? The ideal, no. So that's 0. Do I have any mass leaving my balloon? So the change in mass with respect to time is equal to the mass reacted. Negative, okay? So again, we pull that volume. The volume of my balloon didn't change. dc dt is equal to minus k c v. So think about my parcel. My parcel doesn't change. Okay, the volume of my parcel, the volume of my balloon doesn't change because I have no mass entering or leaving. So volume cancels, and again I end up with the same expression. dc dt is equal to minus kc. And if I integrate this from C0 to Ct, and from time t 0 to time t, I end up with that same expression, ln c over c naught is equal to minus kt. The next set of slides actually go through this same thing that we just did. So think of this, here's my parcel. The volume of my parcel doesn't change as it moves down the pipe, or my balloon doesn't, volume of that, my balloon doesn't change as it moves. So we could think about it as, if we go, here's the red cedar. And let's say you decided to kayak from the MSU campus to the Grand River, where it joins the Grand River, and all the way to Lake Michigan, and out into Lake Michigan. And you're going to kayak all the way through. And on your kayak, and I'm not, that you are on your kayak, you're carrying a reactor. Okay. And you're going to kayak down. And your reactor's closed, so there's no mass entering or leaving. Eventually you get out in Lake Michigan. So you're finally out here with your reactor. It didn't change in volume. So the concentration here is a function of the distance you traveled and the velocity at which you traveled, or the time that it took you to get from here to here. That's what we're describing with a plug flow system. So your control volume is this parcel of fluid. Okay. And I think I've probably explained this, hopefully, enough that you can see that this is the equation we'll use for a plug flow system. So now let's go think. Again, we have essentially the same system. So we have, think of it as a pipe. And the solution is entering at 100 milligrams per liter. The volume in this reactor is 500 cubic meters. The flow rate entering is 50 cubic meters per day. So it's leaving at 50 cubic meters per day. And it reacts according to first order kinetics. So we showed that with a CSTR, using these conditions, we would end up with a concentration leaving of 28.6. So what is the concentration leaving the plug? Is it 28.6? Is it greater than? Is it less than? What do you think? So is it 20? Okay, we have one brave soul, 28.6. Anyone else want to redraw? We've got this pipe. The volume is 500 cubic meters. Q is entering at 50 cubic meters per day. Cn is 100 milligrams per liter. K is 0.25 inverse days. Q out is 50 meters cubed per day, and we want to know C out. We have this parcel here. So we're looking at this parcel of fluid as it moves down the reactor. So the change in mass with respect to time. So you're thinking about this parcel. We have no mass in is 0. So there's no mass entering this parcel. There's no mass leaving the parcel. And the only change is due to the reaction. So again, we have V dc dt because the volume of our parcel is unchanged. And that's equal to minus K CV. V cancels. We end up, and I'm just going to skip the step. Okay, so when we integrate, we end up with this expression here. T is our detention time. This is TD, or detention time. Exactly, the parcel acts like a mini batch reactor. That's exactly what it does. So think about the canoe. If you had a mini batch reactor and it was in your canoe, okay, and you simply transported it down the river, okay, that's exactly the situation. So it really is, it acts as a mini batch reactor. And TD is equal to 500 cubic meters divided by 50 cubic meters per day, and that equals 10 days. So C is equal to 100 times e to the minus 0.25 inverse days times 10 days. Make sure your units are consistent. It's less. Okay. It should be less. Thanks for doing that. Okay. So let's think back. Okay. So one reactor, we had 28.6. Two reactors, we had 19.6. 10.8, if I remember right. 10 reactors. We get 10 point. Here, with our plug flow, same volume. So the volume is constant in all of these. The total volume is constant in all of these. We have 8.2. And with a batch, we allowed it to go. If we had done the batch and we had done it for 10 days, we would have come up with the exact same answer. We just allowed the batch reactor to continue for essentially an infinite amount of time. So if you think about it, as we increase the number of our reactors, the system behaves more and more like a plug flow reactor. So the more reactors we put in series, the closer it approximates the plug flow reactor. If we had 20, okay, we would approach that 8.2. So we should be back, and we have this situation here. We have water that's treated, okay, before being discharged into a lagoon. So we've got a wastewater treatment plant. We're doing some sort of treatment, and then we discharge it to a lagoon. So here's our lagoon. The lagoon has a volume of 5,200 cubic meters. The flow rate in is 0.015 cubic meters per second. We're going to make the assumption that Q out is the same. Otherwise our lagoon, the volume of our lagoon is increasing. So the lagoon's been operating for months, and it's operating so that there's a steady state concentration of 250 milligrams per liter in the lagoon. So that's my C0. And then there's a plant upset. And the upset results in a fourfold increase in the influent concentration. So if the lagoon is operating at steady state, based on what we've talked about, that influent concentration, this is a as a salt, it's non-reactive. So the influent concentration has to be 250 milligrams per liter. Does that make sense why that would be the case? So your salt is non-reactive. So it increases fourfold, so it's 1,000 milligrams per liter. So we have, what doesn't matter what's happening in this wastewater treatment plant, but we have 1,000 milligrams per liter coming in after we've had this upset. C sub 0 is 250 milligrams per liter. The volume is equal to 5,200 cubic meters, and Qn equals 0.015 cubic meters per second. And Q out is the same. The system boundary doesn't include the wastewater treatment plant. If I had written a different problem, the system boundary perhaps could include wastewater treatment plant, but it didn't. So the system boundary is just around the lagoon. And this is our control volume in the lagoon. So the change in mass with respect to time is equal to mass in minus the mass out. And if we had a reaction term, it would include the reaction term, but we don't since it's non-reactive. We're assuming the system is completely mixed, so we'll assume we have a CSTR. And we've assumed that the volume is constant. So if volume is constant, I can write dC, volume times dC dt is equal to C in Q minus C out times Q. And if I integrate this expression from C0 to C and from time 0 to time t, I end up with this expression here. So this is the expression we've developed on Monday. We don't have steady state initially. So if we plot this here, so time 0 is when we had the upset. So this is our plant upset. Change colors here. Before the upset, the system is operating at steady state at 250 milligrams per liter. There's now an upset. So what happens? The concentration increases, and it's going to increase to 1,000 milligrams per liter. So if you simply plug in time, okay, so the conditions we have, C0 is 250 milligrams per liter. Okay, and the Cn is 1,000. So that's what occurs at the plant upset. And I'm just going to. So before the upset, we were operating well. We have this upset at time 0. We initially have non-steady state conditions. And then concentration increases. And eventually, if we don't get the plant operating well and quick enough, we would end up at 1,000 milligrams per liter. Does that make sense? So then the next question I asked, which I won't go back to, we see that here. The next question I asked was, okay, so the plant operators are able to restore operation to the plant, and they can decrease the concentration back to 250 milligrams per liter. So let's go back to this equation here. So we start out with, I'll change colors just to, okay, so to get the plant operating, we're right here. It's reached steady state. So there, C0 is 1,000 milligrams per liter, but Cn is back to 250 milligrams per liter. So at that point, what happens? It's going to decrease, the concentration is going to decrease back to 250. So if we allow it to reach steady state. So we're operating at 250. It's operating well. We have a plant upset. So if we allow it to get to steady state again, we're at 1,000 milligrams per liter. Now we restore the system and we're back to 250. So we'd have a curve that would essentially look like this. Okay. All right, let's call it a day. What I think I'll do is I'm going to set up the next problem. We'll just do it as a poll at the beginning, just to make sure that you've got this, the concepts correct. When you're doing the homework, draw a picture. When you've got everything on ln kappa, it's common to just try and start plugging numbers into the calculator. Draw the picture. It will make your life so much easier. The picture, exactly. Easy to overcomplicate things without a picture. Draw the picture. I can't emphasize enough. As you're working through the homework problems, don't skip that. So let's call it a day there. Thank you. And I will see you tomorrow morning.